Hello everyone. Today I'm going to discuss the second part of tutorial 9. The thing is that tutorial 9 is not actually a very easy one at all. It's not easy at all. So in my previous recording, which was tutorial 9 part 1, I discussed questions from question 1 to questions 3. But today I'm going to concentrate on question 5. I'm going to miss on question 4 because this material is even more difficult than the one which is contained in the question number 5. I think that this should be pretty enough for us. Sorry, pretty enough for us to discuss only topic concerning question 5. So it actually can be split, today's recording can be split into two subtopics. The first one will be triple integrals. Some people prefer to call them volume integrals. So the second name is volume integrals, but I prefer to use triple integrals. What are these objects, how to calculate them, and so on. Then we are going to discuss so-called flux integral. But you know what, flux integral actually a very large topic, and so I'm going to concentrate only on some particular case which can be tackled with the divergence theorem. So let's highlight it from the very beginning. Divergence theorem only. So this is a very beautiful and relatively easy case. So I'm going to discuss only this case. This case you can find this in question 5 of your tutorial sheet. As for question 4, it also has the assignment to calculate flux, but this could be done in a very much more difficult way. Maybe one day, a little bit later, maybe a week later, maybe 2 weeks later, I'll be able to record tutorial on this topic. But I can assure this it's quite difficult, much more difficult. Okay, and finally, in today's tutorial, we are going to use some let's call them nice properties of double and triple integrals. Nice properties, not all of them, but only nice properties of double and triple integral, because these properties can be very helpful when it comes to calculation. Sometimes you know how to calculate your triple integral, but you might get bored with all these, calculations, simplifications, too many of them. There can be too many of them. That is why it's nice to know some beautiful properties, which can considerably reduce the amount of calculations. Okay, so let's start. Oh, I forgot to use my usual pen. Sorry. So, okay, so the first topic will be triple integrals. What are these guys? Triple integrals. How do they look like? Judging by the name, we should see like 3 integrals in a row put next to each other. So you can see three integrals, some function of 3 variables here, because everything is going to happen in 3D space this time, unlike in the case of double integrals. And here you can see some letter, maybe T, V, capital T, it doesn't matter which letter, letters can be different. And here you can see either 3 differentials, or some people prefer to use like something like dt or dv instead of these 3 differentials. So I'm not even lazy to rewrite it. So you can see something like dt, dv, doesn't matter. And besides, this letter here in the differential, here they shouldn't be the same. It's just by coincidence that I use the same letter t here. So what is this t? So that's how you can recognize this, that you are dealing with the case of triple integrals, just 3 integrals next to each other. But what is this t here? T is the region, but unlike in double integral, it's 3D region already. It's like volume in space, 3D space. So it can be denoted something like this. There is some region, 3D region. It has 3 dimensions. So this is why sometimes people prefer to call it a volume integral instead of triple integrals. So, as usual, question arises as to how we can calculate these triple integrals. The general idea about calculation is the same as in double integrals. How did we calculate double integrals? We just needed to transform it to so-called repeated integral, and after that we knew how to deal with repeated integral. Sorry. Here the idea is the same. So your triple integral integral should be transformed to repeated integral. Repeated integral. This time, this repeated integral will contain three integrals, three integrations in a row, of course, as you can already guess. Okay, so the idea is pretty clear, but how exactly do we need to calculate? If you remember, and of course you should remember because you just said test 2 last week, so your memory should be quite fresh. When it comes to double integral, we should have a closer look at the shape of our region of integration. And in relation to this, I highlighted you three cases when the region of integration is suitable for transformation to repeated integral. The first case was when you squeeze your flat region of integration between two vertical lines. The second case was squeezing between horizontal lines. And finally, the last case was about using transforming to polar coordinates. So these were three standard cases which you needed to spot when you wanted to make this transformation from double to repeated integral. What about this 3D case? In 3D case, of course, things look a little bit harder at first glance, but in reality, you could see some analogies. So, what is the shape of this volume in 3D space should be so that you would be able to make this transformation, transition to this repeated integral? So I would say that your volume should have a form of building or the house. Let's call it house. Every house has vertical walls. So this is the first requirement. Your house should have vertical walls. So house, let's call it house. House or building, it doesn't matter. House. So the first requirement is vertical walls. Vertical walls. One of the first surfaces which bound your 3D volume should be, vertical. The next requirement, your house should have so-called roof, which is determined by some equation. Z is equal to Z2 of xy. This is like a surface in 3D space. This is how the usual equation of the surface looks like. It's some function Z of x and y. So you have roof with the equation of Z is equal to Z2. And finally, you have a floor. You have a floor in this house. Let's call it floor. It's not necessarily flat floor like in conventional houses where human beings live. It's just, can be some surface. So the roof, both roof and floor are not necessarily flat. They could be very fancy. They could have very fancy forms. So let's suppose that it has equation Z1. So floor has equation Z is equal to Z1 of xy. And the last requirement is that if you project your whole house, so this is our whole house, very strange house. If you make a projection onto x or y plane, you can see some flat region D. I can even write this region, plot this region somewhere in a separate coordinate system. So this is our D. The T plays the role of projection of our house with the roof, floor, and vertical walls onto x and y plane. Okay, so if you noticed that your area of integration, your region of integration, 3D region of integration has this shape, it means that you're very lucky. You can make this transformation to triple integral. Let's denote this integral as I capital as usual, because I'm too lazy to rewrite it all the time. So how this transformation should be made? When you write the first two integrals in the repeated integral, you look only at the region D. So let's suppose that our region D was squeezed between two vertical lines. You have the options, three options here. Remember, to squeeze it between vertical lines, between horizontal lines, and the last option is to go to polar coordinate system. So let's suppose that our region D was squeezed between two vertical lines. In this case, you know how to write your repeated integral. The external limits of integration will be constants, A and B. These are vertical lines. The next, you have this lower boundary and upper boundary of your region D. So, as you can see, the first two steps are quite similar to those which you took when dealing with a double integral. But now the time comes to discuss the last integral, which is, we can rewrite our function, by the way, immediately here, put dz here, and now we need to tackle this guy. It turns out that your lower limit of integration should be the equation of your floor. So let's write floor here in green. And the upper limit of integration of dz should be your roof. So roof is z2 of xy. And that's it. So that's how this rule of transforming your triple integral into repeated integral looks like. So we can put a frame around it. And now we can do some exercises. But you know what? I want to note that the first two steps are actually crucial, because the first two steps, that's exactly what you used to do when dealing with the double integral. And that is why, even though I wrote here this particular order, I started with dx and then I performed dy. But actually, if you feel that it's more convenient to squeeze your region D between two horizontal lines, it means that here at the beginning will be dy, and only after that you should write dx. That is why let's put some parentheses here and say that the first two integrals are written over region D, and only the last step is something new compared to double integrals. To perform the last step, you should look at the space, a 3D space, and see the floor of your house and the roof of your house. Okay, so let's try and do some exercise. It's not a good page. So what is my first exercise which I prepared? Here it is. So let's call it exercise 1. Exercise 1. You are asked to calculate triple integral over region B 8xyz dv. Look at the notation. So as I said before, sometimes they denote the triple integral like dx, dy, dz, but sometimes just dv or dt or something like this. Okay, and the region B is bounded by following surfaces. We should call the surfaces. X is between 2 and 3. Y is in between 1 and 2. And finally, Z is between 0 and 1. So that's how they give you your 3D volume B this time, not T, but B this time. So let's try and plot it. This is the most difficult part, probably, because no one is a good artist, That is why sometimes it's not easy at all. Okay, let's start with X. X is squeezed between 2 and 3. So let it be 2 and 3. So I need to put two vertical lines here, because X is equal to is equal vertical line. What about Y? Y is squeezed between 1 and 2. So Y equal to 1 is here, Y is equal to 2 is here. And I put two horizontal lines. So you can already have this region. As for Z, is squeezed between Z is equal to 0 and Z is equal to 1. So these are actually two horizontal planes. And finally, our whole region of integration looks something like orthogonal parallelepiped. Yeah, it's like a box, like the ordinary box. So I don't know, I'm not a good painter, as I said, not a good artist, but maybe I can plot it in yellow. So this is my region of integration. This is B. This is B. Let's call it B. So what can we do? What do we need to do to be able to calculate this integral? First of all, we need to plot the projection of our region onto x and y plane, even though we can see it here. This is region D, remember from our notation. But nevertheless, it's better to have a separate plot. So let's start again. X is squeezed between 2 and 3, and y is squeezed between 1 and 2. So this is actually a rectangular region D, which is squeezed between vertical lines. So, and now we need to look at this region B, 3D region B, from the viewpoint of the house. Is this a house or not? That's we need to to come up with a verdict if it's not if it's a house or not. First of all, you can make a spot that this area, this region, does have vertical walls. Of course, these planes are vertical walls. Okay, so the first requirement is met. What about the roof? I can explicitly see the roof. The roof is this absolutely flat, by the way. We are lucky. We are dealing with a very small case. And the equation of this surface is z is equal to 1. This is a typical equation of the plane, horizontal plane. Okay, what about the floor? Do we have a floor in our house? And the answer is yes, we have a floor. Floors here. This is actually region D. And it has equation z is equal to 0. You know what? I realized that my plot is not correct at all. So my region is bounded by this. Very messy, very messy. I made a mistake plotting it, but maybe you'll plot it better. Okay, it doesn't matter. What really matters that I did spot. I did manage to spot the floor, which is green one, and I did manage to spot the roof. And I realized that this building has vertical walls. It means that my region D does meet the requirements, all the three requirements, and it can be called a house or building or whatever. This actually plot is much more crucial. This region, which is projection of the whole 3D region onto XY plane, is much more important. It's much important to plot it more accurately. As for this one, it can be quite messy sometimes. The most important thing here is your imagination. Use your imagination to realize. Some people even prefer not to plot these 3D regions because it's super difficult. Okay, so the most important fact is that we did realize that our region B is a house. And that is why, let me rewrite my integral here. Triple integral x, y, z, dv. So I can make a transition to repeated integrals now. So to write the first two integrals, I need to look only to this region. Of course, it's super easy to squeeze it in between two vertical lines from 2 to 3. So it's dx. The next step is to realize what is the lower boundary of this region and what is the upper boundary. Again, we are very lucky with this particular example. The lower boundary has equation y is equal to 1, and the upper boundary has equation y is equal to 2. Both boundaries are just horizontal lines. So the next integral goes from 1 to 2 dy. And finally, the last integral, I can rewrite my function here already, dz. This time we need to look at our 3D plot, or maybe to our imagination only, if you didn't manage to draw something reasonable here. So the lower limit should be our floor. So z is equal to 0, as you can remember. And the upper limit of integration is our roof, which has equation z is equal to 1. So it's from 0 to 1. And now we can do these calculations. We can do this calculation. So we start with integrating over z, and then we put these limits, and then we move to the second step, to the second step. You know what? I'm sort of lazy to do it for you. I think that you can easily manage it yourself. I'm only going to give you answer. The answer should be 15. And you can pause the video now to practice your techniques of calculation these triple integrals. So I don't fancy spending too much time today. I wonder if I can use. Oh no, I can't use this side. Okay, let's better consider some little bit more difficult example, just a little bit more, a little bit fancy, because this house in example was too simple house. Both roof and floor were flat, vertical walls. We just had everything. We didn't need to wreck our brains over it. Let's try out maybe a little bit more interesting example. So I'm giving you a triple integral again over region V, and this time I'm not giving you concrete function. You know what? To avoid these calculations, all we need to do only to make this transition to repeated integral. And after that, it's not so interesting for everyone. I think that you can easily do all these calculations, and I don't fancy spending so much time of my video on it. Okay, but I need to give you surfaces which bound our 3D region V. So these surfaces are x is equal to 1. You know, this is not a line. When you are talking, when you are inside a 3D space, it's not line already. It's a plane. It's a plane with the equation x is equal to 1. So the next surface is x equal to 2. Again, this is another plane. y is equal to 0, y is equal to x squared, and z is equal to x squared plus y squared. Look at this. We have even 5 surfaces bounding our region. Looks a little bit scary. But you know what? My recommendation is to start with not the 3D volume itself. Let's start with this projection. You know how can it be done? When you look at these 5 surfaces, you can easily get scared. You say, wow, 5 surfaces, that is too much. But what can you immediately notice that some of them, namely these 4, they don't contain letter Z at all. That is why they all could be viewed as lines temporarily on the coordinate system x and y. So let's start doing by pretending that these 4 guys are not surfaces. They are just lines, some curves, on x and y plane. And that's how can we start. And after that, it will be much easier to make the transition into 3D space. So let's have a look at the first one. What is this? This is x is equal to 1. Quite pretty easy. This is vertical line. What is x is equal to 2? It's another vertical line. What is y is equal to 0? This coincides with our x-axis. And what is y is equal to x squared? Of course, everyone knows this is our famous beloved parabola. So that's it. And you immediately get this bounded region D. Bounded region D. Aha. So we did everything in the opposite way. We were supposed to plot the region V, 3D volume first, and only after that we wanted to plot the projection. But we did it just the other way around. But that's how you should make things sometimes. And now we can realize the following thing. You can imagine that this piece of paper where you have this x and y axis, actually it's not 2D surface, it's 3D surface. You can imagine that there is a third z-axis which sticks out of my paper. And you can immediately imagine that this region actually is just the view from the above to our building or house or whatever it's called. So I can rewrite this region here. And these lines, all these curves, are not actually curved, they are just vertical lines. Because, for example, if you look at this curve of this line, straight line, x is equal to, it's not actual line when you are thinking about 3D space. It's already plane which sticks out of this piece of paper. So let's rewrite this region here in this 3D space already. You can see that I prepared 3 axes here. So it looks something like this. So x is equal to 1, x is equal to 2. Here we had parabola. So this region D looks like this. And you can imagine that there are vertical, these all are vertical walls. They are vertical walls. And finally, what is this guy? It's time to discuss the last guy. This is a surface, very famous surface. I make a separate drawing for this surface. It's a famous elliptic paraboloid, I think. Yeah, the name is elliptic paraboloid. It's like a big cup. So this cup goes here, and it plays the role of the roof of your very strange building. As you can see, I didn't even manage to plot a beautiful picture here. You can use both your imagination and a little bit of plotting, probably. This is the best approach. Because you're not supposed to be a good artist, to draw all these buildings, all these volumes and so on. You are supposed to have a good imagination. Not even good, just mediocre. Imagination is enough. So what is our conclusion? We realize that these surfaces, which doesn't contain letter Z, they are walls. They are vertical walls, actually, because they are all called cylinders, for example. So this is parabolic cylinder. This is just, vertical planes. And this guy plays the role of the roof. Roof, yeah. You know what? I forgot to mention one more surface, by the way. I made a mistake, a little mistake. Let's correct my mistake. There's one more surface. That is equal to 0. And that is equal to 0. This is the, the floor of our house. Floor. And so what can we see? We see that we have a very fancy house, actually. It does have vertical walls. That's okay that one of the walls has a very queer shape, but it doesn't matter. there are some fancy houses in real life as well, not only in mathematics. And it has quite a proper floor. Floor is flat, z is equal to 0. But the roof is very strange. The roof is really strange. The roof is the surface of this cup, But what can you do? There are even fancier regions sometimes in mathematics. So it means that we determined the most important thing. We have a roof, we have vertical walls, this is the first requirement. We have floor, which is z is equal to 0. But remember which color I used for floor, to be honest. The roof was a red one, and the floor was the roof is like this, and the floor is green one. So our building does meet all these requirements. It means that we are able to make this transition to repeated integral. So let me rewrite this integral here again. So this was our given triple integral. And now I start making this transition. So to perform the first two steps, to write the first two integrals, I need to look only to this, only at this region D. So of course it's super easy to squeeze it between two vertical lines, dx from 1 to 2. The next integral is from 0, y is equal to 0, y is equal to x squared, dy. And finally, the third integral, to be able to write the third integral, we need to do what? We need to look at the roof. So the roof should be the lower limit of our integration, not roof, floor, it should be floor. And the roof should be the upper limit. It has the equation x squared plus y squared. So I put it here, x squared plus y squared. Sorry, I made a little bit of mess here. So I need to draw this boundary here. So this is from 0 to x squared. So as you can see, this skill of performing, turning our triple integral to repeated integral needs some maybe practice. So my recommendation for your homework is to go to your study guide. This is page 164, and you have two exercises there, 3.17 and 3.18. These are very good exercises for practicing your skills with the triple integrals. They are not actually very difficult at all. One of them is super easy. Maybe one of them is a repetition of one of these examples. But I think it's better than nothing. Okay, so we are finished with our first topic. And now it's time to move to the second topic, which is flux. Flux integral. It's called flux integral. Flux integral. So what is flux actually? Of course, it was discussed during the lecture, and probably you remember that when you are inside some vector field, vectors everywhere, maybe 3D space, 3D space, of course. And if you put some surface here, I'm drawing something like umbrella. So you can immediately imagine that it looks, the vector field looks like a fluid, some liquid, like water flowing something. And if you put some surface here, the water will flow for this surface. And we can calculate, we might be interested, I would put it this way, we might be interested in the amount of water which goes out of this surface in this direction, or maybe in the opposite direction, in some period of time. So this amount of water is called flux. Flux of liquids, flux of vector field, of course. So, and generally, we have a formula for flux. Flux can be calculated by applying so-called surface integral, which sounds really scary. So you need to know your vector field F, then M ds, or dA. It's dA and S. So I wrote the formula for you now. Formula for flux. This is actually the definition of the flux. But now it's time to discuss what is this guy. You know what? F is your vector field, of course. So the F is our vector field. Nothing fancy, nothing new about it. Vector field. What is this S? S is a given surface. You are interested in the flux of your vector field through this surface. So this is your surface. This is symbolic notation of your surface. What is n? N is a vector, normal vector to your surface. You know what? Normal vector can have two directions. It can point either this way or maybe this way. What does it mean? the direction of your normal vector shows in which direction your water is moving, in which direction you are interested in the flux. If you're interested in this direction, you are interested in the water, amount of water going in this direction. But you know what? It means that if you get your result flux, your flux negative, it means that in reality the water flows in this way. You were interested in motion in this direction, but it happens in the opposite direction. So flux can be both positive, negative, and even zero. Sometimes it happens so that nothing flows through your surface. Okay, but you know what? The whole object, it does look like a double integral, but the looks can be deceptive. It's not double integral anymore. This is a so-called surface integral. Surface integral. It's quite a new object for you, and I have to admit it's not quite an easy kind of integral. But luckily, you don't need to, so far in this tutorial at least, you don't need to know how to calculate this surface integral. It's absolutely new object for you. Again, as before, as with the case of double and triple integrals, it takes some time to, even to get used to it, let alone applying it to some, some tasks, some problems. Okay, luckily, we are going to discuss only some particular case. It turns out that if if your surface S is closed, is closed, then this flux integral can be rewritten as triple integral. So this is a very likely case, triple integral over region T. And you, instead of function, you have to use divergence of your vector field. And let's put dt here. So this is a very nice particular case. And this transition from the surface integral to this triple integral is called divergence theorem. This is a very famous Ostrogradsky-Gauss divergence theorems. So this formula called divergence theorem. Divergence theorem. This is a very nice case because you're already familiar with the triple integral, and you don't need to master this fancy surface integral. But it's only for a while. It's only temporarily. As I said before, the objective of this tutorial, this recording, is to discuss question 5 from tutorial. But the previous question 4 was exactly about this surface integral. So maybe one day in a week or so, I will record another tutorial devoted to the previous question 4, which is a real surface integral. But so far, just get relaxed. You already know everything about triple integral. It's not so difficult as you realize. It's okay. You know what? I gave you this formula, these divergent theorems, but I need to give you some maybe to draw some plot. What is this T? And what does it have in common with this S? So idea is that your surface S is closed surface. I don't know how to plot it repeatedly. So you can imagine some volume T, and it has surface S. So you're interested in the flux through the surface S, and you're interested in the external side of your surface. That is why I put my normal vector here. So in this case, if you're interested in the flux of your liquid, not liquid, but vector field, of course, we should say, through the closed surface, and namely through the external side of this closed surface, which is indicated by the this vector n, normal vector n. In this case, you can apply this beautiful divergence theorem. You don't need to know anything about surface integral. All you need to do is to be familiar with triple integral. Okay, so now let's try and apply this theory to some concrete task. Maybe it was question 4, question 5. I'm not sure now that it's question 5, but nevertheless, let's start doing it. Probably it was question 5. I'm not sure myself. Okay, so in question 5 from our tutorial sheet, we have this surface integral. They give you surface integral. The assignment is that you are asked to calculate this surface integral. They don't use the word flux. You are supposed to recognize that, oh, this is flux, of course. This is flux of this vector field. And the surface is bounded by, determined by the following inequalities. X is between 1 and 0. Y is in between 0 and 3. And Z is in between 0 and 2. And the vector field F is given by vector x squared is the first component, the second component is z, and the third component is y. So our task is actually to calculate the flux, because the flux is given by this integral according to the definition, through this surface determined by these inequalities. But maybe you already recognized this surface because we already dealt with it in our example 1 in the very beginning of this recording. So this is again just a box. This is just orthogonal parallelepiped. So we can plot it, of course, but luckily it looks like we are dealing with a very simple case. So x is between 1 and 0, y is between 0 and 3. And we can start drawing this box. And 0 is between, z is between 0 and 3. So we are dealing with the box again, and box is undoubtedly building. It does require all, it does satisfy all the three requirements. It does have vertical walls, it does have a roof, so our roof is definitely this, and it has equation z is equal to 3, because this is just a plane, horizontal plane. And of course it also has a floor, which is determined by the equation z is equal to 0, because it's a flat surface. Okay, so no. I started talking about building too early, because we didn't just realize how to deal with this surface integral. It's not a triple integral yet. It's just a surface integral. Look at this. But you know what? We are asked to calculate the flux through the whole surface of this parallelepiped, the whole surface. And the whole surface, of course, is closed. And that is why we are very lucky. We are able to apply this beautiful divergence theorem. All we need to do, we need to calculate triple integral over this volume, which is determined by this closed surface S, which is inside this closed surface S, from divergence of our vector field, and that's it. So we need to calculate divergence first. Let's calculate divergence somewhere here. So divergence of our vector field F is what? We need to take the, maybe it's better to write it somewhere here. Okay, so divergence of vector field F is determined by the formula dp over dx plus dq over dy plus di over dz, where p, q, and r are components of our vector field. So let's calculate it. So the first derivative is 2x, the second one is 0, and the third one is 0 as well. So our divergence is just 2x. So we need to calculate triple integral of function 2x over our parallelepiped. And now we can easily make this transition to the repeated integral. I think it's super easy for you. So the first integral, we need to look at the region D first. Let's plot it separately. It's always a good idea to have a good region D. So x is between 0 and 1. Y is between 0 and 3. So this is our rectangle D. So it can be, the easiest approach is to squeeze it between vertical lines, is usually x is equal to 0 and x is equal to 1. So dx will go from 0 to 1. dy will be between 0 and 3 dy. And finally, we rewrite our function here to x and put dz here. And now it's time to realize what is the floor and what is the roof. So the floor, of course, given here in green, z is equal to 0, and the roof is equal to 3. Roof is equal to 0. And that's it. And you can finish this task by repeating this integral. I don't know what the answer should be. I'm not sure. It's written like 6. The answer should be x, 6. But you can look at your tutorial sheet to make sure. But I'm pretty sure that it was 6. So as always, I'm trying to save my tutorial, my recording time, but not making these calculations. It might be really boring, and maybe it's better for you to do that. Also, homework. The next portion of the homework will be to finish this problem, and also you can do study guide again, page 165, and exercise 3.21. This exercise is just about divergence theorem. Okay, so we are finished with the second topic. And now it's time to discuss the third topic, which had quite a nice name. Some nice properties of double and triple integrals. Let's call them this topic again the same way. Nice properties, some not yeah, nice properties of double and triple integrals. I'm just write them in this manner. So let's start with double integrals because these properties are very similar ones, and it's better to start our discussion with double integrals. Let's call it topic 3a. 3a. What is this nice property about? Of course, both double and triple integrals, they have quite a few, quite a big number of properties. But I'm talking about only one of them now, the nicest one. So it turns out that if you are dealing with the double integral, right, dx. By the way, double integrals sometimes are written not like this, like I used to write before, dx and y. Sometimes they put some letter, dd here, dt, or something like this. Look at this. What is interesting about this double integral? It looks like the function is missing here. Of course, it's not missing. It's actually equal to 1, of course, this function. But mathematicians are very lazy. They never write 1. So it just looks like empty integral without function. But in reality, you know that it's just 1. So this nice property says that if your integral, double integral, looks like this without the function, with function being equal to 1, it means that it's equal to the area of this region. Very nice property, actually, if you come to think it. So it gives us the method of how to calculate the area of some flat region, and x on y plane, of course. And at the same time, this property can be used in the opposite way, in the opposite direction. So that's why I decided to give you this topic, because it's super interesting and super nice to know that sometimes you don't need to make this boring transition to repeated integral. You can just use this property on the fly. Very beautiful idea. So let's start with the first example. No, not the first example. It will be like example 4 probably. I lost count, to be honest. Let's imagine that you need to calculate integral over region d7 dx dy. So, and your region looks something like this probably. So this is a triangle. Here you have 1, here you have 2. And so this is your region D. And of course, so far you've known only one method. You've known that, of course, I'm dealing with double integral. I'm given this region D. I need to make this transition to repeated integral. It's quite a little bit boring, of course. You need to squeeze it between maybe two vertical lines. Maybe it's better to squeeze it between two horizontal lines. But you know how to do it. But you know what? Instead of doing all these things, you need to realize. So this integral can be easily rewritten in this form if you pull out this 7 constant. So let's pull out 7 outside the integral, and you immediately get something very, very familiar. So the whole guy is actually equal to the uh, area of this region D. And you know this is a good news because we know how to calculate the area of the triangle. You know the formula probably. So the area of the triangle is 1 over 2 times A times B, where A is this side and B is the height of our triangle. So in our case, so instead of doing all these boring calculations, we can just use the formula for calculating the area of the triangle. So at 1 over 2, so this side is 2, and this vertical side is 1, and that's it. So we immediately can get the answer. So now you can see how beautiful this property looks like actually. And it's especially impressive when you are dealing with some circles, because circles are especially annoying when it comes to calculating double integrals over circles, because circles are quite difficult to be integrated, and you always need to make this transition to the polar coordinate system, which is quite a long story actually. So let's imagine that we have another integral, like maybe over d3 dx dy, and your region D is actually some circle, x minus 2 squared plus y plus 1 squared, less or equal than 1. What does it mean? I think that we can know this region. Maybe you recognize that this is just a circle, and the center of the circle is point with coordinates 2, -1. So it's 2 and x is -1. So this is the center of the circle and radius is 1. So our circle looks like this, and the region is everything inside this circle. And so, and usually, normally, it's quite a boring story because once you see the circle, you immediately realize, oh, I need to make this transition to repeated integral, but before that, I need to do it in the polar coordinate system, which is quite a long story. But look at our integral. Just like in the previous case, we can pull out our 3 and we immediately obtain this beautiful integral, which is always the area of this region, which is now, in our case, this is the area of the circle, and you know the formula PR squared, and r radius, in our case, is just 1 squared. So and we immediately obtain the answer, 3 pi, that's it. So you can see how beautiful it goes sometimes. Sometimes you might be real lucky. And it's really handy. It's really, helpful, because otherwise you might spend so much time just calculating all these things. And the more calculations are involved, the more prone you are to making careless errors, which is quite frustrating. So I hope that I managed to convince you that this is a really nice property, and that is why, inspired, we can move to our very last topic, 3b. Let's call it 3b. The same beautiful topics, but only about triple integrals. Something very similar happens to triple integrals. So if you are given triple integral over some 3D region T, and there's nothing inside this integral, there's nothing. No, it's not nothing. It's just a function which is equal to 1. But it looks like there's nothing. It means that you are dealing with the volume of this region T. So it looks pretty similar. The only difference that everything happens in 3D space, and that is why it's not area of region here, it's volume of this region. So very beautiful property, actually. And it's even sounds even nicer because, as you can imagine, as you suspect already, that calculating repeated triple integrals is quite a long story, of course. And if you all of a sudden you notice that you're dealing with such a beautiful case, it means that, oh, you're so lucky. So let's do a couple of exercises. Exercise 6. Let's imagine that we are given integral. No, as I said before, it's not necessary to write dx, dy, dz. Sometimes we write something like dv. Look, let's write 3dv, just for a change, just for variety. And your surface, not surface, but your region, 3D region, is determined by this inequality. X squared plus y squared plus z squared is less than or equal to 4. You are supposed to recognize this equation or inequality. This is a sphere. This is sphere with the center in the origin, and the radius is equal to 2. So sphere, I don't know how to plot it, so maybe I managed to do it. So this is definitely a sphere, and we need to calculate this integral, triple integral. But of course, we already realized that we can pull out this 3 out of this integral, and we're immediately dealing with this form, which means that this integral 3 times is actually equal to the volume of our sphere, And of course, you're supposed to know the formula for the volume of the sphere. It's 4 over 3 p and radius cubed. So in our case, it will be 4 pi, and radius is 2 cubed. So it will give us 32 pi. Look at this. So watch out for these cases, for these beautiful cases. Every time you need to calculate triple or double integral, always remember about this nice property. What if you're lucky? If you're not, of course, then you have no option but to make this transition to a repeated integral. But always watch for this as the first, as the first method. Let's do one more exercise. So let's imagine that we are given integral over region T, and I'm writing dx, dy, dz just for variety. Sometimes I give you triple integrals in this form, and sometimes in this form, just not to get used to one form only. Okay, so and what if our surface is cylinder, some cylinder? So let's do a cylinder. like this. So in your not the surface, your 3D volume is the cylinder. Cylinder with the radius, like I don't know, radius is equal to 3 probably, and the height is equal to 5. Of course, you immediately realize that instead of making this boring and long time-consuming transition to triple integrals, you're very lucky that your integral has a 1 as a function. And that is why it's just equal to the volume on this cylinder. And of course, if you know the formula for calculating the volume of the cylinder, you are super lucky. So it's pi radius squared times the height of the cylinder. In our case, it will be 3 squared and 5. 9 times 5, 45 pi. So that's it, as you can see. So I hope that I managed to convince you that it's a good idea to know this nice property because it might save you a lot of time, just a lot of time. And you know what? I have a very good exercise for you in study guide again. Study guide, study guide. This is page 165, and this time it's exercise 320. 320. In exercise 320, you are asked to calculate the flux for the surface, for the closed surface. But when you calculate the flux, and you can, it means that you can make the transition divergence integral. So you're actually dealing with 3D, triple integral. But the thing is that your divergence turns out to be constant, some constant. I don't know, it's not necessarily 3, it's some constant. And it means that you are dealing with this nice property. You can use this nice property to finish your task very quickly. So that's it. So that's it for this tutorial.